The reactions are slow because the bonds are really strong, and also the geometry involved. So if you look at the complexity of the molecules, if we have sodium ions, chloride ions, that's just like 1-to-1. It's pretty easy for them to hit. There's not a lot of complex geometry going on. But if you have C12, like a big hydrocarbon with oxygen, this collision is not simple. All right. Later on in this chapter, we look at reaction pathways. All right. The more complex the molecule, the more complex the geometry, the harder it is to get proper reactions, or proper collisions, I should say. Okay. So if you have simple atoms or molecules, you get a fast reaction. And then, why am I writing in yellow? A fast reaction, especially this is just an electron transfer. It's an ionic bond. Okay. But when you look at this combustion reaction, there's a lot of stuff happening, bonds that need to be broken and formed. So the more complex the molecules, the more complex the nature of the reactants, which leads to more complex collisions and pathways, i.e., you get slower reactions. All right. And then there is surface area, which only applies to solids, right? So if you have, I think I talked about this briefly, if you have a chunk of metal or something, only the stuff on the outside is able to react. Whereas if you divide it up a little more, then these molecules or these atoms here on the inside, which were in, maybe I'll do it on the video. All of those on the white lines are no longer in play because they're inside the chunk of metal. But if you slice it open, all the stuff in here now can be attacked from whatever you're reacting it with. And ideally, if you grind it up into a powder, it's almost like an infinite surface area, right? There's tons of things that can combine. So like if you slice it up, it's like a lot of atoms. Yeah, I mean, theoretically, if you break it down into its individual atoms, that's the ultimate, right? But that would be an aqueous solution, essentially. So the finer, the smaller the surface area, the faster the reaction is going to be. So increasing the surface area equals increase in the increase in the reaction rate. But it's only true for heterogeneous reactions. Okay? So, no, there's a T, there's a cross there. All right? So what this is if you have zinc, zinc chloride, AQ. This is heterogeneous because you have a solid and an aqueous solution. Okay. Homogeneous would be something like AgCl solid. It's the same state. Okay. All that knowledge. So heterogeneous reactions. Different phases, different states. Yeah. But we're talking mostly about solids here, right? You can increase the surface area here. Surface area doesn't play a part here, even though you have a solid, because this is a product, right? Okay. I want to get to calculating reaction rates today, just because that's what we're going to do tomorrow. But so we're going to rip through the next two. Okay. Next page, please, people. The phases of a reaction. So There are 4 phases. Does anybody know what the phases are?
Aqueous, solid, liquid, gas.
Okay, aqueous, solid, liquid, and gas. All right. Aqueous is the fastest. Okay. Shh. Do we know what aqueous means? You're dissolved in water. Okay. So silver ions floating around like the reaction I just showed you, chloride ions. All right. What do you think the next fastest would be? Gas. Why would gas be the next? They're spread out, but why are they spread out? Why are the molecules further apart in a gas phase than they are in a liquid or a solid? What? They're moving really fast, which means they have more kinetic energy, right? Which is what you need for collisions. Gases. Then, what do you think's next? Liquid. And then solid. Okay. All right. Just a couple of side notes. Shh. Homogeneous phases are faster than those in heterogeneous because homogeneous, you're in the same phase, you can get close together and react. Whereas if one is a solid, like this, solid and aqueous, like I said before, surface area can increase this, but not all the atoms will be exposed. Okay? So as long as they're homogeneous, it's going to be a faster reaction than the heterogeneous in terms of if it's equal. So if I had silver ions reacting with chloride, that should be a chloride ion. Actually, let's do this. If I went okay, if we go silver ions reacting with sodium hydroxide, but I dissolve the sodium hydroxide in water. Okay. And then I have in another beaker silver that is aqueous, but this time sodium hydroxide is like a pellet, all right, in pure form. It's just a pellet. We dissolve it in water to create the base, all right, in concentration. Which is going to be the faster reaction? Top one, right? This is a homogeneous reaction because they're in the same phase. They're aqueous. They can get really close together. This is a solid and an aqueous. Part of this is going to be hidden inside of the solid ball or its actual bead. Okay. So this would be the faster reaction. All right. And then the final one is a catalyst. All right. So they increase a reaction. Well, I've heard, okay. I would say a catalyst and an inhibitor. Those are pretty self-defining things. A catalyst is going to speed up the reaction. An inhibitor inhibits the reaction and slows it down. There are some textbooks that'll say a positive catalyst and a negative catalyst. And when they say a negative catalyst, they mean an inhibitor. But I think that is, I don't like that wording. So I will say catalyst and inhibitor. Okay? The thing about catalysts is it is not consumed. You get it back at the end. Okay? So, the catalyst is not used up in the reaction. You can recover it. Now, it might be hard to recover it, but you can recover. So you have seen this reaction. What's H2O2? It's written weird there. That's hydrogen peroxide. Okay. It naturally decomposes to water and oxygen. In the uncatalyzed form, it is very slow. That is the, if you've ever seen hydrogen peroxide, it's the little bubbles that are forming. That's it decomposing. Okay, it's just slow. You can add a catalyst. The way you write a catalyst is you write it over the little arrow here. In this case, the formatting isn't great, so it just writes it right over top of it. And it increases the reaction rate exponentially. It's like instant, basically. This is elephant's toothpaste, this reaction. You remember this reaction?
Yeah.
The big foaming hydrogen peroxide that goes everywhere? That's this reaction. Okay? The only reason you add, you know how you add the liquid soap, right? That is just to capture the gas so you get the bubbles forming. It looks really cool. Okay? That's all it is. But the actual catalyst is manganese oxide. Okay? What they do is they lower the activation energy. Okay? So if you have, this is the normal reaction for it. A catalyst lowers the activation energy. Okay.
Wait, so is lowering the activation energy including
Threshold?
threshold? Is that
Yeah. For us, yeah. All right. So it lowers the activation energy by helping to orientate the molecules or providing a surface where the reaction to take place. So you sort of limit the amount of geometry that needs to happen. Okay. That's what enzymes do. Anybody in biology here?
Yeah. Oh my god. Oh my lord.
Wow. So basically, enzymes are catalysts. All they do, have you studied enzymes in biology yet? Like they just grab the molecule and they orientate it perfectly so that it exposes the right part to be attacked. Most of the reactions in your body won't happen at a fast enough rate without enzymes. Okay? Athletes will take enzymes, special enzymes to speed recovery, all these sort of things. It leads into all this nutritional supplements and all this kind of stuff. All right? So, catalyst, two things with a catalyst. You get it back at the end and it lowers the activation energy. Okay? Inhibitors lower the rate. Okay? They sort of block things. Okay? This is how sort of poisons and stuff work. All right? Biology people, have you studied the electron transport chain and Krebs cycle and all that kind of stuff? Look at the looks on your faces when I say these words. It's like, oh. Okay, tricarboxylic acid cycle. Is that better? TCA? All right, it's all the same thing. Okay, so cyanide. Did they tell you? Sorry? No, I'm not telling you how to make. It's not that hard. Cyanide's in like, what is it, almonds?
Apples.
Apple seeds and almonds too, isn't it? Yeah. Yeah. Anyway, I'm talking to the biology people here. The electron transport chain, did you learn about that? NADH, FADH2, ATP, all that fun stuff. So, did they tell you how cyanide works? Why does cyanide kill you? Thank you. So what cyanide does is, yeah, I'm not going to ask you this, but this is just a side note. The electron transport chain, so basically at the end of the Krebs cycle and all those things, you make your reduced cofactors, the FADH2 and the NADH. Doesn't matter what it is for you guys. They dump the electrons into what's called this electron transport chain, which is a bunch of complexes. The electrons flow through it. There's almost like this, like, I don't know how in depth they went with you, but as the electrons flow through it, like turns and clicks, and it spits out. Tell me, I can't remember. Sorry.
What is it? Carbon dioxide.
Carbon. Yeah, it's respiration essentially, right? So you breathe in oxygen and CO2 comes out here, or something like that. I can't remember the exact thing. It's been about 20 years since I did this. But anyway, what cyanide does is this would be way more dramatic if this worked. Is it blocks the electron transport chain. Why? Okay, so it puts a big block into it. So all these electrons build up, and you can't breathe. Respiration does not occur. And then that's why you pass away fairly quickly. Okay, that's all cyanide does, is it blocks that and essentially halts respiration in your body, which shuts down pretty much everything. Okay? But sunscreens are good inhibitors, right? Because they're blocking the UV light from damaging your cells. What do they call it? Apoptosis? Cell death? Apoptosis, that's it. Thank you. So you inhibit cell death. All right. Okay. So what do we need to remember? Temperature affects the rate of all reactions. If you can increase the temperature, you will increase the rate. For every 10 degrees, thank you, increase in 10 degrees Celsius equals times 2 the rate. Pressure/volume affects reactions with gas as the reactants. Gaseous. Decreasing the volume equals increase or decrease of pressure. Increase of pressure. Concentration, so if you increase the amount or the concentration, only affects aqueous or gas. All right? It does not change for pure liquids or solids. Surface area only affects heterogeneous mixtures. All right? And then the other thing you should remember is the aqueous is faster than gas, is faster than liquid, is faster than solid. Okay. All right. I'm just going to stop the video and create a new video.